Hello everyone, and welcome back to another Civi 398 ABAQUS tutorial. In this ABAQUS tutorial, we're going to talk about something new, and that is contact. So in our previous models, they were actually pretty simple in that the only real complexity that we had was we had a hole in some of our parts. Now it's going to get a little bit more complex in that we have a hole within our parts, but we actually have multiple parts, that being a plate as well as a bolt. Now, where the complexity gets even greater is that we actually have to define some contact between the plate and the bolt, because if we don't define any sort of contact between them, as you guys will see, they'll just go right through each other, which of course is not realistic at all. So before we begin, I just want to emphasize again, this ABAQUS tutorial does not play into the assignment whatsoever. You guys do not need this one for the assignment. This is just little fun facts about ABAQUS in case you guys are more interested. All right, guys, let's look at the model. Alrighty guys, so looking at our plate, we can see that it's a very simple plate. It has two holes in it, and it has material properties that are very similar to that of steel, with the Young's modulus being 200,000 MPa and having a Poisson's ratio of 0.3. If we look at the geometric properties of the plate, we can see that the plate thickness into the page is 200 millimeters, and referring to the figure above, we can see that there are two punched holes in the plate, and each one of those punched holes has a diameter of 15 millimeters. Now remember that with this plate we are actually going to add bolts into those holes of the plate, and the diameter of the bolts is 14.6 millimeters. So it's important to keep in mind here that the diameter of the bolts, it's slightly smaller than the diameter of the holes into the plate. And once we define these bolts, which are going to be defined as rigid, we are actually going to pull the plate and see how the plate makes contact with these bolts. So this is going to be the key here to the models, defining that contact between those bolts that are shown as the purple circles and the plate, which of course is shown as the plate. Now, before we begin, just one last thing I want to show. Referring back to the last ABAQUS tutorial, if we look at the loading conditions of this plate as well as the geometry, we can actually see that it is symmetric about the x-axis. So if we want to save some of that computational time, which is always nice, what we can do is we can actually only model the top half of the plate, or if you guys want the bottom half of the plate, and apply a symmetric boundary condition. So that's what I'm going to do in the model, and I just wanted to make that aware before you guys wondering what I did with the second half of the plate. Alrighty guys, let's jump into ABAQUS. Alrighty guys, welcome to ABAQUS. Now before we begin, just a quick reminder to save your model and set your work directory. It's always good if you want to look for your ABAQUS files a little bit later. It's always a nightmare trying to figure out where they went if you didn't save your model. Alright, so if we look at our model, the procedure of creating the model is going to be almost identical to that of the previous models, with some exceptions thrown in because of the contact. But the first part, just like in the previous models, is we want to create our parts. Now, unlike the previous tutorials where we only had one part, this particular example has two parts, the plate as well as the bolt. So we're actually going to have to create two parts in this module. So to create a part, I can either go to parts here, or I can click the button, it doesn't matter which one, and you'll be greeted with the menu that says create part. Now the first thing it's going to ask for is what you want to call the part, and typically if you guys only have one part, it doesn't really matter what you call it because it's very easy to tell which part it is. But once you're dealing with multiple parts, it's good to have a good naming convention so that you don't get anything confused moving forward. So it says, what do I want to call this part? Well, if I'm doing the plate first, let's call this part my plate. I know that my plate is going to be a two-dimensional plate, and it's going to be a shell feature, so I'm going to go continue. Now we're in the menu where we can start drawing the plate, and we know that the general outline of our plate is a rectangle. Now just a little reminder from the theory, we are going to utilize symmetry to save some of that precious computational time. So I'm actually only going to create the upper half of the plate, but luckily for us, it actually looks identical to the bottom half of the plate. So if you guys want to think that I'm doing the bottom half of the plate, it doesn't really matter because they are going to look the same. So again, the outline of the plate is defined as a rectangle, so I can go to the rectangle button over here. It's going to ask me to specify a corner, so starting at the bottom left corner, I'm going to enter the point -50, 0, so over here, and then we know that the plate comes up to the top right corner, which is defined by a coordinate of 150, 50. So this is going to be our plate right here. And some of you guys are saying, Clayton, why did you offset it by a factor of -50? Well, it's because I'm going to put the whole of the plate right on the y-axis over here. All right, so we have our plate, but if we want to put a hole in the plate, we have to go to the circle option. So I'm going to click circle option. It's going to say, all right, what's the center of this hole? Well, we know that this is going to be located at 0, 22.5. So this is going to be the center of the hole. And what I'm going to do is I'm going to specify the left corner of the circle. I guess it doesn't really have a corner, but I'm going to specify this point going along the x-axis on the left side. So we know that this is going to be negative 7.5, which is basically the diameter divided by 2. And it's going to have the same height, so 22.5. And I'll have my hole right here. Now, referring back to the plate, this is all that we actually needed to do. So I'm going to say I'm done creating my shape, so I can click exit, which exits me out of the create circle command. And now that I look at my section, it is good to go, so therefore I can go done. Now I have the top half of my plate, or if you guys want to, I have the bottom half of my plate. So therefore the plate is good to go. But as I mentioned, we need two parts. So if I expand down the parts tab, I have my plate, but I also need to define my bolts. So what I'm going to do is I'm going to create another part here, and under name, I'm going to call this one my bolts. Now, we mentioned that these bolts are actually going to be rigid bolts. They don't really have material properties. It is going to be treated as rigid. So instead of a deformable type like we did with the plate, we are actually going to go to discrete rigid over here. You guys can do analytical rigid, but that actually requires some other things, which I'm not going to get into this tutorial. So I recommend just going discrete rigid. And under feature, we are going to go wire. So I'm going to go continue. And all we have to do for these bolts is basically draw a circle. So what I'm going to do is I'm going to go to the create circle command. We know that the origin of the bolt is just going to be 0, 0. It doesn't matter where you create these bolts. And we know that the bolt, of course, has a diameter of 14.6 millimeters. So that is a radius of 7.3. So my second point is I'm going to put 7.3, comma 0, click enter, and therefore I have now defined my bolt. So I'm good to go. I'm going to click exit, and then I'm going to click done over here, and I have my bolt. Now notice that my bolt isn't solid because we actually don't need this area inside of the bolt. This is a rigid surface, so it's wherever the bolt makes contact with, it'll be able to make that contact, basically. You don't need anything inside because since it's rigid, we're not going to analyze any of the stresses or the strains in the bolt because there isn't no strains in the bolt. Again, it's rigid. All right, so if we look at our parts module here, we're good to go because we created two parts, our plate as well as our bolt. So with that good to go, we can go into our next module, which is the property module. So again, because this bolt is defined as rigid, it actually doesn't have material properties because it is rigid in nature. So if we go to our parts here, right now it has us at the bolt. Well, we don't care about the bolt because it's rigid, so we're going to click that and go down to our plate because this does have material properties that we are actually going to assign. So the first part is we have to create those material properties. So I can go up here to create material, or I can go to materials on the model tree, double click it, and it's going to say, all right, what do you want to call your material? Well, actually, let's call it steel. Typically, I call it elastic, but for this specific case, since it's basically steel, we're going to call it steel. And we know that we're just defining an elastic material. So I can go mechanical, elasticity, and then elastic. All right, so it's going to ask for two things, the Young's modulus and the Poisson's ratio. Well, we know the Young's modulus is 200,000 MPa, and the Poisson's ratio is 0.3. So that's actually nice and simple. I can click OK, and now I can see my model tree that I have my material property for the steel defined. Now, before I apply this material property to the part here, I need to define a cross section for the part. So I'm going to go sections. What do I want to call this? Well, it's going to be the plates cross section. So I'm just going to go plate, keep everything as default, continue. What material would I like to add to the section? Well, it's going to be our steel material. And we know that the plane stress / strain thickness into the page was specified as 200 millimeters. So I'm going to click OK. And now that we see we have a section defined, which I called plate. Now what I'm going to do is I'm going to take this section that we just created and I'm going to assign it to this part. So under here we can go assign section. It's going to say, all right, select the regions to be assigned. Well, I'm going to click on my plate here. It gets nice and highlighted. I click done and it's going to ask me what section I want to apply. Luckily for us, we only created one section, so it's pretty easy to pick which one you want to apply. From here, it's going to be plate, and I'm going to click OK. And if you guys did it right, it turns into this nice green color. All right, so now that we have our material properties defined, we can move on to the next step. So I'm going to come up here to the modules, and we can see after property, we have the assembly tab. Now, the assembly module is actually the most easy for us in the previous tutorials because we only had one part. But now that we actually have two parts, it's going to be a little bit more complicated, but as you guys are going to see, it's not too bad at all. So we can import our parts into this model space here by this button here that says create instance, or we can go down to the assembly tab on the model tree, expand it, and double click instances. Now it's going to say which parts do you want to import, and before we only had the one part, so it's pretty easy to tell, but now that we have two parts, we can either import the bolts or the plate. So what I'm going to do to start is I'm going to take the plates, I'm going to go OK, and as we can see, we have imported one instance, which is the plate. But we have more than one instance in our actual model because we need the bolt in there as well. So I can double click instances to add a second part here, and now I want to import one of the bolts. So I'm going to click bolt. As we can see, it specifies it right there at the origin, but I can click this auto offset from other instances to kind of move it to the side so nothing's really intersecting at this point. So I'm going to go OK, and now under our actual model, we can see that we have two different parts. We have our plate over here, and we have our bolt. Now this is a problem though because our bolt is off to the side of the plate. It's not in the actual hole where we want the bolt, so we're going to actually have to move that instance. Luckily for us, on the tab over here, there's a button that says Translate Instance. I'm going to click that. It's going to say select the instance to translate. I'm going to come over here to the bolt. I'm going to click it. And this is the only one I want to move, so I'm going to go done. It's going to say specify basically the start point. Well, I want to move the center of this bolt starting from here, and it's going to then ask, where do you want this center to now be? Well, I want it in the center of this hole over here. So I'm going to click over here. And as we can see, it now moved my bolt all the way from here into the center of the plate, or the hole of the plate. Now, what's going to happen is it's going to just ask you to confirm that this is what you wanted. This is, so we're going to click OK, and we are good to go. Now, if you made a mistake and said no, what'll happen is it'll automatically push the bolt back over to here, and you guys can then start again. But from here, we are actually good to go. So it's kind of hard to see, but we have our plate, and if we scroll in, we have our rigid bolt in the center of that plate hole. All right, so this is basically it for the assembly tab, because again, our model only consists of two parts, and we've added those two parts and specified the position of those parts. So what we can do is we can go to our next module. So I'm going to click assembly, and the next module is going to be step. Now, by this point in the ABAQUS tutorials, you guys are very familiar about steps, so I'm not going to bore you too much. So I'm going to double click step because we know that we want to create a loading sequence for this beam. So what I'm going to do is just call this step load, go continue. I'm going to switch on nonlinear geometry. But unlike the previous models, I'm actually going to add some incrementations. So what this incrementation is basically the percentage of the load you want to apply per step. So by default, ABAQUS has it set to 1, which basically means it's going to apply 100% of the load in basically one step. So if I'm applying 10 millimeters of displacement, ABAQUS is going to go from 0 millimeters all the way to 10 millimeters. Now I can specify this fraction as something smaller, so instead I'm going to go 0.1 as the initial and as the maximum. And what this means is instead of going from, let's say, 0 to 10 millimeters, this will go from 0 to 1 to 2 to 3 to 4, etc., all until it reaches that 10 millimeters of displacement. So it's just making this go a little bit slower instead of trying to load so much at once. Now, this is actually very important. I'm not just doing this for shits and giggles. What happens here is once this surface makes contact with this surface, it actually becomes very hard for ABAQUS to analyze. And if I were to ram the two surfaces together, it's going to create a lot of numerical problems, and we don't want that. So whenever you guys are dealing with contact, we need to go for a much slower incrementation so that the surfaces can make contact nice and subtly, and then we can start to see the stresses after that. All right, so if you guys were to try and load this all at once, I guarantee that there would be a little bit of unsuccessful incrementations in your guys' model. All right, so now that we're done with the step tab, we can go down and we see that we now have interaction. So this is going to be the key here. We never dealt with interaction before, but now that we have two parts that are going to make contact with each other, this is when we actually have to deal with the interaction. Now, the first thing that we have to do, and this is because we chose a rigid surface rather than a deformable surface for the bolt, is we actually have to specify a reference point. Now, what this reference point does is this basically defines the movement of that rigid surface. So I'm going to click here for reference point. It's going to say, where would you like to put this reference point? And this doesn't matter. I can put the reference point anywhere I want in the model. It's not going to make a difference. But for simplicity, I know that this reference point is actually going to be tied to the rigid bolt surface. So I'm going to put it at the center of the rigid bolt. And it's that easy. Once you click on your spot, you'll have a little notification saying you created a reference point. Now what we actually have to do is we have to say this reference point here actually represents this rigid surface of the bolt. So we can do that in a couple of ways, but the best and most easy way for me is create constraint. So we can either go constraint over here, create constraint, or we can come down here into the constraints tab. So I can double click that. And what it's going to say is what kind of constraint do you want to apply? Well, we know that we're actually dealing with a rigid body right here. So I'm going to go down to rigid body. I'm going to go continue. Oh, and this menu looks really bad because of ABAQUS being so zoomed in. But it's basically going to ask for two things. It's going to ask for what surface do you guys want to tie for what reference point. So what I'm going to do here under body elements, what I'm going to do is I'm going to select it in the viewport. And we know that we want to tie this analytical surface, this rigid surface here, to that reference point. So I'm going to click on the surface. I'm going to click done. It's going to say which reference point you want to couple these two. I'm going to come down to our only reference point right here. And from here, we can see that the body has been picked. The reference point has been picked. So therefore, I am good to go. Now, some of you guys may be saying, Clayton, what exactly did you do there? What does this constraint mean? Well, what happens when you're dealing with a rigid surface like this is you actually don't apply any sort of loads or displacements to the surface itself. You apply it to the reference point. For instance, what we are going to do is we're going to fix this analytical surface here. But we don't do that by selecting the surface and fixing the actual surface. What we actually do is we're going to fix the reference point. Now, since this reference point is tied to the surface, every point on the surface will now be fixed. And that's exactly why we are going to do it. All right. So what we're going to do now is we're actually going to move on. But it's very important to notice that we actually didn't define any sort of contact interaction between the plate and the bolt. And what I want to do is I want to show you guys first what happens if we don't define any of that interaction. So we're just going to carry on right now, even though we should have defined the interaction. And if we look, we see that our next step is actually the load module over here. Alrighty guys, sorry about the weird cut. A fire truck decided to go by and make a lot of noise, so I thought I might as well just get rid of that and start the load module step over again. Alright, so when we're looking at our load module, we actually have a couple things that we want to define. The first of which is going to be what we want to do with this bolt here. So we know that we want the bolt to stay stationary or fixed in the same position during the entire analysis. So what I'm going to do is I'm going to go to boundary conditions here. I'm going to create a new one. And what I'm going to call this one is simply fixed bolt. Because again, I want to fix this bolt into the same location. I don't want it to move once I start moving the plate. So how I can do that is I can either restrict the displacement over here, or I can actually go up here to this encastre because this basically means fixed. So I can go continue. Now what I want to do when I'm selecting the bolt here is I actually don't select the surface of the bolt because remember we tied this surface of the bolt to the reference point. So what I'm going to do is I'm actually going to select the reference point here. I'm going to click done, and then from here I can fix the reference point by clicking this last option over here. So since we fixed the reference point of the bolt, we basically fixed the entire surface of the bolt. So even once the plate starts making contact with the bolt is not going to move, therefore the plate will start to actually deform. So that's what we're going to do with the bolt. Now, we know that in order to create some sort of contact, we actually need to pull this plate. So we're going to create another boundary condition, and this is going to be the displacement of the plate in the lateral direction. I don't know why I couldn't figure out the word direction. So I'm going to go displacement. This is going to be my boundary condition. And since this is basically loading the plate, this will go into the load step. I'm going to come down to displacement over here. I'm going to click continue, and it's going to say which region would you like to displace. Well, that's going to be this end region over here. So I'm going to go done. And what I'm going to do is I'm going to apply a lateral displacement of, say, 10 millimeters to the end of this plate. So if we look at our boundary conditions now, we have two, where we basically fix the bolt as our first one, and then we pull the plate laterally as our second one. Now remember that when we look at the original geometry of this plate, it was actually two bolt holes, and what we said is since it was symmetric, we can only model the upper or lower half of the plate, save some of that precious computation time. But in order to do that, we actually have to tell ABAQUS that it is symmetric about the axis. So what I'm going to do is I'm going to create a third boundary condition, and I'm going to call this one my symmetric boundary condition. And since it's initially there all the time, this will go into the initial step. And of course, it's a symmetric boundary condition, so we're going to click the first option where it says symmetry. I'm going to go continue, and I'm going to say that this piece of the plate here, this is the top half of the plate. So therefore we know we have the identical thing, or the identical shape on the bottom side of the plate down here. So what I'm going to do is I'm going to click this line of symmetry, go continue, and we know it's going to be symmetric about Y. So I'm going to click continue. Therefore, I have my third boundary condition, which basically states that this plate is symmetric. And this part up here, this is the upper half of the plate, and then down here would be the lower half of the plate. So now that all of our loads are done, we can go into our next module, which is of course going to be the mesh module. Now this is very important because typically we only had one part, therefore we only needed to create one mesh. But now since we have two parts, we actually have to define a mesh for both the plate as well as the bolt. So I'm going to go over here to my parts, and under my first part, it automatically gives me the plate and say, all right, this isn't too bad. We are going to seed it. And as a default, it has it as 10 millimeters as of the approximate size. That's a little bit big. Let's go down to 2 millimeters. Looks a lot more fine. Should be pretty good. I'm going to go OK for 2 millimeters. And then I'm going to mesh the parts. So I'm going to click continue. And of course, it gives me a mesh like this. Now, in these tutorials, the mesh doesn't really matter. We're not going to get too deep into what is a good mesh, how to make a better mesh. This is something for you guys to explore if you guys go to graduate school. So although this may not be the best mesh, we're going to assume that it's just fine for the purpose of this tutorial. All right, so now that we have the plate meshed, we can't forget that we also have to define a mesh for the bolt. So under this parts tab, I'm going to click the expanding menu, and I'm going to go to my bolt. So here is my bolt, which is just a nice wire. I'm going to do the same steps where first I'm going to seed it. It has an approximate size of 10. Well, that's extremely large because that won't really take into account the curvature of the bolt. So let's put that down to 1. And now we can see that that is a lot better. So we're going to click OK with 1. And then we are simply going to mesh the parts. So is it okay to mesh? Yes, it is. And therefore we can now see our mesh around the bolt, which is perfect because now we have both of our bolt and our plate meshed. We can actually analyze this object. So in our module tab, we're going to go down to job, and we are going to create a new job over here. Again, you guys can double click the job button if you guys want, and you guys are going to name your job. So I'm going to call it analysis 1. Well, I've called analysis 1 all the time. Let's go analysis 2 just to shake things up. It's going to bring you to this menu. Don't worry about this menu. You're just going to click OK, and we can see that we've now created a job called analysis 2. So what I'm going to do is I'm going to right click it, and I'm going to submit it for analysis. All right, so before we look at the results, I want to make extra clear that under our interactions, we actually didn't define any sort of interaction between the bolt and the actual plate. We tied the bolt to a reference point, but we actually didn't specify any sort of contact. Now, the reason why I didn't do this is because I want to show you guys what happens in ABAQUS if you guys don't specify the contact. So our analysis is complete. I right click and go results. We have our plate, and of course, since it was symmetric, we see the plate as a whole, and this is the undeformed configuration. So what I'm going to do is I'm going to zoom in. We can see that we have our plate here, we have our bolt over here, and once we start applying the load, we can see, I need to go over here. We can see that the plate actually just goes right through the bolt. So this will be a little bit better in slow motion. Maybe I can highlight, I don't want the element, I want the it's not letting me select the element. But basically we can see our bolt here, and we can see that once we start applying the deformation, it just goes right through the bolt. Nothing really happens at all. So your analysis won't crash if you guys don't define the contact, but of course it won't actually model the contact. So we're going to fix that right now. So we're going to go back into our model, and under our module, we're going to go back into the interactions tab. Now under this tab, the only thing that we did was we tied this rigid bolt surface to this reference point, but now we are actually going to start creating some of those contact properties. So the first thing that we actually have to do is define the contact properties itself, and that is found down here under interaction properties. So what I'm going to do is I'm going to double click it, and it's going to say what kind of property do you want to have. Well, we know that we want a contact property. So what I'm going to do is I'm going to call this bolt contact, because why not? We know it's going to be a type of contact, so I can go continue. And then you guys are going to get met with this menu. Now, if you guys remember the material properties menu, it's actually very, very similar, but this one's actually a little bit more simplistic because it doesn't have so many options. Now, contact properties that we're going to be dealing with for a structural basis include things like hard contact as well as friction, stuff like that. So these can all be found in the mechanical tab over here. And we basically deal with two for the majority in structural applications, and that is tangential friction and normal behavior. So the key one for us is going to be this normal behavior. It's going to have it as default hard contact, and we are just going to leave this be because this is all we're going to need. Now, if you guys are interested in friction, of course, that'd be in the tangential behavior, and we can actually specify a friction coefficient, stuff like that, but this will make your analysis become a lot harder to analyze. So we're going to actually skip the friction. We are just going to have simply that hard contact. Basically, when two surfaces meet, they're not just going to go right through each other. They are going to actually have that contact now. So I'm going to click OK. And if we expand our interaction properties, we see that we actually have a bolt contact property. But again, just like the material properties, is we just created a property. We haven't actually assigned it into our model. So if you guys remember the material properties, we actually went into the sections tab, created a section, and then applied it to our parts. And we're going to do something kind of similar here, where we're going to go one above, which is interaction. So we created an interaction property, but now we are actually going to specify an interaction. So I'm going to double click it here, and it's going to say, what do you want to call this interaction? So let's call it bolt to plate, because this is what we're dealing with. We're just going to keep it in the initial step, and we have a couple of options: general contact, surface to surface, self-contact. But for this case, we have two surfaces that are coming in contact, so we are going to go surface to surface contact. I'm going to click continue, and then down here it says select the master surface. All right, so what happens when you're defining contact between two surfaces, you're going to be asked for two things: the master surface and the slave surface. And as some of you may guess, this is referring to the surface of the bolt and the surface of the plate. Now the question becomes, which one is the master and which one is the slave? Well, in general, the more rigid one, or especially if it is rigid, that will be the master surface. So since our actual bolt is rigid here, the bolt will be our master surface. So if I hover over the bolt, we can see it becomes highlighted. I'm going to click it. I'm going to go done, and it's going to say which side is going to make contact. So is it going to make contact on this yellow outside, or is it going to make contact on this, it says magenta inside? Well, we know that the plate is going to hit it from the outside, so we are going to go the yellow side over here. Now, just like I mentioned before, it's then going to ask, all right, select your slave surface. So I'm going to go, my slave is a surface, and it's going to select the region. Well, we know this is going to be the whole of the plate. So I'm going to select that whole of the plate, which is now pink, and I'm going to go done. And then from here, you're going to get this big crazy window. But the only thing that you guys really want to make sure is this down here. So contact interaction property. This is what we just defined as our interaction properties of that bolt contact. If you guys don't define an interaction property, you guys can create one using this button over here. But if you don't have one, this will be empty and you guys won't actually be able to create the interaction. But since we've already created our interaction, we are good to go. So we're just going to leave everything default and click continue. So if you guys did it right, what you guys now see, it's kind of hard, but there's little squares on the surface of the bolt as well as the surface of the plate. And this means that there's now contact defined between them. So initially, they're not in contact, but once we start moving the plate laterally, it's going to make contact over here. And since we now define that contact, it's not just simply going to pass right through the bolt like it did in our first analysis. So now that we've defined the contact, we can come back down to our job and we can resubmit it, now knowing that we've had the contact defined. All right, with the analysis now complete, we can check out the results. So I'm going to right click and go results. We can see that we have our plate before any deformation. And remember, last time after we applied the deformation, the bolt would stay the same and then the plate would just pass right through the bolt. But now that we've defined that contact, hopefully the contact will occur and then we can see some bearing of the plate onto the bolt. So what I'm going to do is I'm going to click this button here that says plot contours on the deformed shape. And as we can see, the contact is now initiated with the bolt and the plate. We can see that we have a lot of stress concentrations where the contact is being made, which of course is expected. And then we can see some of the elongation of the plate hole because of the contact with the bolt. So that's how you guys do basic contact in ABAQUS. Now, I'm emphasizing basic because, of course, it gets a lot more complex than this, especially when we start dealing with friction. Friction creates a lot of numerical nightmares that are very hard to describe. So for you guys' instance, where we're just showing you guys kind of the cool features of ABAQUS, this is sufficient, but keep in mind that it does get a lot more complex than this. So thank you guys all so much for listening. I really appreciate all your guys' support on these videos. I will see you guys in the next tutorial.